Thank you. Thank you so much. Hello, everyone. Thank you very much for joining us with this event. And good day, good morning, good afternoon, depending upon wherever you are. It's my absolute honor to have Dr. Roger Melko as our invited guest speaker today. Roger is a professor at the University of Waterloo and a faculty at the Perimeter Institute for Theoretical Physics. And he's the Canada Research Chair in Computational Quantum Many-Body Physics. He received his PhD from the University of California in Santa Barbara in 2005, and his undergrad was in physics, and he earned that in 2000 from the University of Waterloo. Roger's research involves the development of computer strategies for the theoretical study of quantum materials, atomic matter, and quantum information systems. He was the recipient of the 2016 Canadian Association of Physicists Rydberg Medal for achievement by an early career physicist. Since 2017, Roger is collaborating with Vector Institute for Artificial Intelligence in Toronto as an affiliate faculty, and also he's a chief scientist at Creative Destruction Lab, again in Toronto. Roger is here to tell us about designing quantum computers with generative models. Thank you so much, Roger, for your time and for being here. I'm really, really excited to learn more about designing quantum computers from you.
Great. Okay, thank you so much, Reza. Very nice introduction. Welcome everyone to my talk. All of you joining me out there all over the world. As Reza mentioned, I'm going to talk about designing quantum computers with generative models, and this is research that's being performed in sort of my extended group at the University of Waterloo, including experimental collaborators at the Institute for Quantum Computing, which I'll mention, and also the Perimeter Institute for Theoretical Physics, where I head sort of our quantum computing and artificial intelligence lab, which we call the Perimeter Institute Quantum Intelligence Lab, with the acronym PICL. So I'll show you some of the PICL research. This is the PICLers pictured in obviously better times last year before the pandemic hit, and now we're largely a virtual institute. So before I get into kind of the nitty-gritty of the generative models, I want to talk a little bit about what quantum computers are, and just as by way of a very sort of brief introduction, I just want to show pictures of these two gentlemen, and to kind of frame the ideas, two of the main ideas behind quantum computing. So these are quotes. The first one by Richard Feynman: "Nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." I mean, there's a lot there to unpack, including the use of the word golly. But what the point with this quote is that Richard Feynman, and others in sort of the early 80s really pictured a quantum computer as something that is used to simulate aspects of nature, or emulate aspects of nature in sort of a highly controlled environment. And this speaks to my line of research in condensed matter, materials physics, and essentially foundational quantum many-body theory, because there are many unsolved and problems and sort of unexplained phenomena that happen when you get many quantum particles together and let them interact. And this could be things from the mechanism behind high temperature superconductivity, or the desire to design higher temperature, room temperature superconductors. It could be quantum chemistry, understanding reaction rates, all sorts of applications of the quantum many-body problem. And what Feynman was sort of promoting was the idea that in order to solve for these intrinsic quantum systems, it makes a lot of sense to emulate them with a highly controlled quantum device. Okay. And so that's his idea behind, a simulation of nature. And Peter Shor, the gentleman on the bottom, who I got this quote from, when I was working on my quantum algorithm for factorization, I didn't tell anybody because it seemed like such a long shot. I think I just got that off his Twitter feed. he's a fun guy to follow. Follow him on Twitter. What Peter Shor demonstrated in the sort of early and mid 90s was something a little bit different than what Feynman was promoting. And that was the idea that quantum computers, or, maybe more accurately, quantum logic in sort of a digital gate-based device, can solve problems in the classical world, okay? Like problems that we encounter, like factorization, that have difficult solutions, classically, but may have, essentially a scaling change in the computational complexity for quantum devices. So there are different motivations for building quantum hardware. And just as another way of introduction, these and other motivations have led to different types of quantum computing hardware. Oh, and I've just listed kind of the three main, what I would call the three main categories of quantum, what we call computer. And my definition of computer is very sort of broad. It's really just a highly controlled quantum device that we have, access to, that we can prepare states, manipulate states, look at the unitary evolution, look at other types of evolution, perform readouts in a controlled way. And the first category, what I'm calling analog simulators, are sort of true to Feynman's original as vision as a platform I'd say simulate, but to differentiate from, computer simulations, I could also say emulate many-body quantum systems in a highly controlled platform. Okay. And I'll show you lots of data from quantum simulators, including trapped ions and cold atom simulations. So as I mentioned, there's many applications. I mean, we really want to understand, say things like materials, chemistry, even quantum electrodynamics, quantum chromodynamics, very, very sort of foundational aspects of quantum many-body theory. And we're at the age now where we or our friends in laboratories, academic labs and in industrial startups can build these analog simulators to tackle problems that are sort of at the edge of what's prohibitively difficult, I would say, for classical computers. A second type of hardware, which I won't talk about, is the quantum annealer. So this is the sort of architecture popularized by D-Wave, and in an analog simulator. Again, what we're doing is we're trying to emulate a quantum system in a highly controlled environment. In an annealer, what we're trying to do is typically solve a problem, a classical problem like a traveling salesman or an optimization type problem, which is intrinsically classical, right? But we're trying to do that with some sort of quantum advantage or quantum speed up, whether it be quantum tunneling in the annealing landscape or whatever it is. It's sort of a different class of problems in many instances than we're looking at with simulators. Not all instances, but many instances. And as you know, annealing hardware, unlike with Shor's algorithm, where we have proofs, of, if you will, computational complexity or asymptotic computational complexity for certain algorithms, in quantum annealing, there's really no kind of hard and fast proofs for quantum speedups. And there's a lot of, I'd say, very rich scientific debate centered around this type of hardware, which I think is very positive. I mean, companies like D-Wave or private labs that look at annealers are really exploring kind of new ideas in solving for these ground state problems with their hardware. And there's a lot of back and forth between experimentalists and theorists. I'm a theorist, but I love working on experimental data. And this is, again, a rich playground for that. You can argue that this is the easiest hardware to build if you can tolerate a lot of noise and temperature. Or you could say that the first two categories, analog simulators and quantum annealers, are maybe both equally difficult to build, let me put it that way, or easy. The final category, which we typically think about when we just say the word quantum computer, is really sort of the digital, fully fault tolerant, error corrected device that performs highly controlled quantum logic operations, like Shor's algorithm, like Grover's search, things like that. And that's really the holy grail. It's Turing complete in the sense that it's general purpose for classical computations, and you can extend that to many quantum computations. So it's universal in that sense. It requires error correction, but even more strictly, I would say fault tolerance, which means that there's a big overhead between logical qubit and physical qubit. So many physical qubits have to be combined to make logical qubits. Gates in the universal digital whatever gate set have to be implemented on the logical qubits. This overhead results in sort of a much more difficult platform to build than the first two. And so, we're still on our way there. I think the 9-qubit Shor code was like the error correcting code was just demonstrated a couple weeks ago. So the first, I think, robust demonstration, or one of the first robust demonstrations of error correction have just occurred. But we're still in the early stages of this type of hardware. NISQ hardware, noisy intermediate scale quantum hardware, which are sort of the currently existing precursors to this. They're still noisy and they're not error correcting or not fault tolerant. Are another sort of, I would say, interesting platform that is somewhere between analog simulators and these digital computers. And so there's a lot of work happening now on this NISQ hardware. All of these approaches, all of this hardware, whether or not you're talking about superconducting qubits or trapped ions or whatever it is, all of this is dependent on our best classical computers in order to design, control, address, run, and read out the quantum hardware. And this is nothing new. I almost put a slide in about classical computers being designed by classical computers, but I decided that it's probably almost obvious. I have ex-students, for example, an ex-student who works at Intel on automatic defect classification in Intel's fab. And so what she does is basically use the current best available Intel hardware plus the best available software, including machine learning, which I'll talk about, to design the next iteration of Intel's chip, the process, those kind of automated defect classifications that are performed by her group are really on the cutting edge of what current conventional computer hardware is capable of. So you're really trying to design the next iteration of conventional hardware with the current best existing hardware and software, and it's no different in the quantum case. So we are going to require, the best conventional computers, the best high performance computing capabilities, and the most, innovative simulation algorithms to design, characterize, validate, and so on quantum hardware. And so that's where my group comes in. So we have a lot of expertise in simulation of quantum systems, and we're basically turning that more and more into a data-driven endeavor where we have a black box, which is the laboratory quantum hardware. Measurements are performed, and we take our classical computers, say our laptops, and we leverage that data to help try to characterize, validate, and then suggest, if you will, updates back into the experiment. And so this process, which is sort of occurring now, this data-driven process where an experimentalist essentially emails me some data, and then I get back to him a month later with some ideas. This kind of cycle, or this feedback loop, is becoming more and more automated, I would say, as this procedure goes forward. And machine learning is really because this is data driven, because these black boxes, whether they be academic labs or D-Wave hardware or some other industry or commercial hardware, because the data is being produced today on these devices, machine learning is really an important tool for this. So I just want to talk about one specific sort of part of the quantum computing stack and how we use machine learning to help characterize and design that. And that's the base layer. And that's what I would call the real sort of hardware, the physical qubits, whether they be, gallium arsenide quantum dots, superconducting circuits, or, clouds of ultra cold atoms or ions trapped in electromagnetic fields and lasers, diamond NV centers. I mean, you could come up with a list of sort of candidate qubits. Also, how they're interconnected, how they, they kind of have crosstalk between each other, how they're stable, their coherence times. All this type of stuff is what we work on largely in my group. But there's a lot more to quantum computing than just studying qubits, obviously. For one, a large sort of effort right now in, I believe, a lot of the quantum computing laboratories is using machine learning for control. And so that is, readout from the physical qubits, and then, suggesting or defining, pulse sequence or other operations that keep qubits stable or perform readout measurements and so on. These are kind of the physical layers. And there's, I think as every month that passes, there's more and more sort of machine learning being integrated into these physical layers of the stack. Above that, because you start getting into sort of more of the logical layers. And the most important one for a general purpose universal device is quantum error correction. So I won't talk about that, but the idea that, you correct quantum errors as they occur with this redundancy or with this overhead to form a logical qubit that I talked about is really the purpose of this layer. And machine learning plays a large role there. As you move up, logical operations, how do you apply gates on fault-tolerant qubits? I don't think it's ever been done. But you start getting into the more abstract layers where you're compiling into universal gate sets from programming languages, and up and up and up into sort of the top of the stack, which could be cloud access and high-level languages and so on. So I'm just going to focus on the base layer of the stack, and I'm going to imagine the quantum computer as just to begin as a device that stores information, and I want to start that conversation by comparing it to how we store classical information, just as one perspective on quantum computing. And as you all know, well, here's a old style hard drive, but as you all know, classical information is stored on conventional computers using bits, right? The classical unit of information. And if I had a hard drive that stored, say, n bits of information, the state of that hard drive, which is just read out by a read-write head, is really just, physically the state of, say, a small magnetic domain. I've just kind of imagine zooming in these circles and say, I don't know, a white square is a small magnetic domain that's spin down and a black square is spin up. And what you do is you translate that into, each one of those into a unit of information. So state of the bit, right? Up, 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 I don't know, down, up, whatever. And, the hard drive exists in one of these specific states, right? So either this is the bit configuration, this is the bit configuration, all of your photos and pictures and emails and everything are stored like this. And I can imagine if I took that hard drive and I wanted to label what state it was in, then I could label that state with just this vector. I've just written it as a vector of all of these bits, whatever all these bit states are. So I don't know, this one's 1, 2, 3, up, down, 2 up, whatever, however I decide on the ordering, that's this vector. So the classical information exists in one of these states. As you know, a quantum hard drive, if you will, works very different. And here's a quantum hard drive that I work with at the Institute for Quantum Computing. It's in Rajabul Islam's lab. It's a trapped ion device. And I mean, just kind of a caricature of it. There's lasers coming in here, and there's a very small electromagnetic trap in this case, because the ions are atoms with an electron stripped off, so they have a charge to them. And those ions can be manipulated with both optical, like laser cooling and trapping and so on, but they can also be manipulated by electromagnetic fields. So how does Rajabul prepare a state in that quantum hard drive? Well, as we have to recognize, the state is, in contrast to the classical hard drive, the state isn't just one of these, if I will, vectors. As we know, these vectors are basis vectors of a larger Hilbert space, and the state of a quantum system is a general vector in that Hilbert space. What does that mean? It means that the hard drive can exist in a superposition of both this state and this state and this state and this state, with coefficients which tell you how much of each one of these sort of basis vectors, or each one of these basis states, contributes to the overall state. And that is the wave function. That is the, that's related to the density matrix, however you kind of characterize this in the quantum mechanical sense. And what I've done is just written this mathematically as, here's a wave function. That's what we call the state of the hard drive, right? And it's the sum over all of these 2 to the n indices or coefficients in front of these state vectors. And so you see that this state of the quantum hard drive is a much more complicated object than the state of a classical hard drive. And let me also point out that these C's, these coefficients, don't have to necessarily be real, right? So in a probability distribution, if you had some sort of probabilistic classical state, these things would be real, and you can interpret this as sort of a probability of getting one of these out upon measurement. But in the quantum case, these are complex. So that leads into, how do we read a quantum hard drive? And as you know, by the measurement postulate of quantum mechanics, a single measurement on that device, however you implement that measurement, you address single ions and you shine in lasers that either give you a fluorescence that gives you a readout from a CCD camera, or you have some sort of microwave pulses that you're using in a quantum superconducting quantum circuit, or however that happens. A single measurement takes the state of that hard drive and collapses it into one of the 2 to the n possible configurations. And keep in mind that this is an exponentially large number, 2 to the n. So if this is what you would measure, again, the information that you receive when you do a single projective measurement is really a classical information where all of those qubits have been projected into one of these states, right? But that wasn't the state of the wave. That wasn't the state of the hard drive. That wasn't the wave function. That was only the result of one measurement. So what Born told us was that, the probability of getting one of these states is from a measurement is equal to the square modulus of those C numbers, those complex numbers which are out in front. And so that's how you relate the probability of a measurement to the wave function, to the state, the actual state of the system. And performing one measurement, as you can imagine, does not give you enough information to know what this probability distribution looks like. You actually have to perform many repeated measurements on a hard drive prepared in the same state to even have a hope of reconstructing that state. And so what I'm going to talk about is how we use machine learning and these projective measurements to reconstruct the state of quantum hard drives, and then basically what we hope to gain from that. So reading a quantum hard drive really means reconstructing the wave function from a large amount of these kind of projective measurements. So to do that, I'm going to use generative modeling. And so let me switch gears a little bit into machine learning, and then I'll combine the two the two threads together. Here is some sort of deep fakes, which have been generated from an unsupervised machine learning technique related to generative models. Okay, so you could read the paper here on the archive, but essentially this captures a lot of what we're doing in terms of the quantum reconstruction. Here are pictures of celebrities, Marilyn Monroe, Einstein. I guess this was Rasputin, from this VoxCeleb 2 data set. So one of these standard data sets used for machine learning. On the left is the actual source images that were taken by a camera. And on the right are generated images that result from a generative model, which, as you can tell, have been manipulated to, so that you can strike different poses from these original source images. So to be clear, there are no, on the right-hand side, there are no pictures that were taken by a conventional camera that correspond to these faces. These were generated from a model, that was trained on a combination of source images, but other data that basically can give you these separate poses. And for the machine learning experts out there, you probably immediately recognize the results of a GAN, generative adversarial network. And this is a good opportunity to just kind of maybe classify very briefly the different types of generative models for the experts out there, because we're going to use a subset of the sort of branches on this tree. Generative models, typically use some sort of maximum likelihood in their cost function, which I'll talk about. And I would say there's two main branches of generative models, which are explicit and implicit density models. And I'm going to talk about that on the next slide. But what this means is you have an explicit representation or an explicit model or parameterization of a probability distribution. And probability distributions, just to go back, are what we're going to be interested in here. Okay. So you can have an explicit a representation of a probability distribution or an implicit one. And again, is in some sense an implicit representation, because as you know, you have this adversarial relationship between the two parts of the GAN. Under explicit density, which is what I'm going to use today, there's approximate and tractable, which in some sense means that you have an unnormalized or a normalized representation of the underlying probability distribution. So I'm going to actually show results from both branches. I'll be using restrictive Boltzmann machines, which use the Markov property for Markov chains for generating, generating, say, these images, right? But I'll also show results from recurrent neural networks, which are mentioned sort of in passing on the left here. And I would also, this is an older paper from 2017, you would also throw things like the transformer over here on the left side. Okay, so why do we care about density or probability and explicit versus implicit and tractable and so on? So it's really again, to go back to my black box, it's really the idea that generative models learn from a data set. So here's my black box, but instead of a wave function, let's just consider a probability distribution, and I'll talk about the difference as we go on. So here's a black box. Maybe it's the internet. Maybe it's your phone. I mean, you're all generating data all the time. This data is however you're interacting with your technology. And if you're generating, say, images and posting them on Instagram or Facebook or something, let's imagine that each one of these vectors here is one of those images. Okay, so the goal of a generative model, which again is a branch of unsupervised machine learning, is to really learn what is the underlying probability distribution of those images that are being generated from this black box. Okay, and that might seem a little counterintuitive, because you could say, well, what is the underlying probability distribution of a cat or a picture, all possible pictures of cats? Or what is the underlying distribution of these images? So it lacks what we would call ground truth in the machine learning sort of industrial setting. But I think the idea transfers actually very nicely to the quantum setting. So again, we have images being produced. Maybe they're black and white. Each one of the pixels of the image I've stripped into a vector here. And I have some data set that's of limited size, because there's some cost associated with these images. So maybe I just threw a number out there, 10,000, because that seems to be something we train on quite a bit. So just imagine that I have some finite set of thousands of images. And what I want to do is learn the best possible approximation, I'm calling it small p, to that black box distribution that I don't have access to. And I also want an approximation that generalizes well to data that's not in the data set, because I have a limited amount of data, right? And so if you want to learn a probability distribution or learn an approximate probability distribution, you can imagine, well, the easiest thing to do is to just look at the frequency of occurrence and build a histogram. And the idea is that with generative models, we don't have enough data. The Hilbert space in our case is too large, and we don't have enough measurement data, or the state space of all possible images might be too large, and we only have 10,000 pictures of cats to really do a faithful reconstruction as a frequency estimator. So instead, what we do is we parameterize the distribution. That's what we're calling a model, and that's where the model in generative models comes from. And the idea is that there's certain models, and they might be things like stochastic neural networks, or they might be things like recurrent neural networks that have things like weights and biases, or whatever the parameters of your model are, that are used to represent that distribution. And the goal is to learn those parameters. So that's the philosophy that we're going to adapt. So again, just looking back at generative models and how we classify them. Again, we're looking at explicit density on this branch, which means that we are going to have, an explicit P of lambda, and lambda is all those parameters. So those parameters are going to be, directly interpretable as a distribution, a probability distribution. And we're going to look at both sides of this branch, the approximate density side, which I will show results from the restricted Boltzmann machine, and the tractable density side, which I will use results from an R and N. So just go back to the RBM, just very quickly. An RBM is an ancient piece of technology in machine learning. It was used as a generative pre-training step before like AlexNet, before modern deep learning, before convolutional neural networks and so on came out. But it's a very interesting piece of technology and something that is very useful for physicists like myself to use to understand generative models. All it really is a Ising model. I have visible units on the left and hidden units on the right, and each one of these units is just an Ising variable that's 0 or 1. I have weights and biases. Weights connect visible with hidden only. That's why it's restricted. Biases occur for every site. We call them B and C. And from this, we form a Hamiltonian or an energy function, which is weights connecting visible and hidden units and biases for visible, biases for hidden. And using, the Boltzmann distribution with no concept of a beta here, keep that in mind. We really see where we have an explicit density or an explicit parameterization of the model using these lambdas, weights, and biases, but we don't know the partition function. And so that's why it's an approximate density. So we basically have to sample from this model using Markov chain Monte Carlo. The size of the visible units is fixed by the number of pixels in the image, or as we go on, the number of qubits, and the size of the hidden layer is kind of a hyperparameter that you vary to see how expressive you are. The recurrent neural network side, so this is now a tractable density model, actually looks a lot different in many ways. Now, instead of having n visible units, we're going to break down the recurrent neural network into, there's a hidden state that we feed in, and then there's the visible state, which is sort of the projective measurement of 1 qubit, or the black and whiteness of 1 pixel, which gets fed into the recurrent neural network. There's different ways that the parameters, the weights and biases, I guess I should call that lambda, kind of exist inside a recurrent neural network. You have GRUs, you have LSTMs. I won't discuss that. What is important is that the output, which is a hidden state, maybe passed through a softmax or something, gives you a conditional probability distribution for the outcome of the next, if you will, pixel on the chain, conditioned on all the previous. That hidden state and the outcome of that probability are then fed into the next iteration of the recurrent neural network. And the reason that a recurrent neural network is tractable density, is because you can use the chain rule to combine all of these individual conditional probabilities like this, starting from defining an arbitrary sequence from qubit 1 or pixel 1, pixel 2, pixel 3, to give the full joint distribution like we're kind of looking for here. And the difference between this distribution and this distribution are that this one is normalized. And that's why the RNNs are a tractable density. So just a little reminder on sort of generative modeling technology. These are sort of the two technologies that we are actually, started with when we replaced pixels with the projective measurement outcomes of quantum computers for the reconstruction. So just to gloss over this, the training of these models really means tuning those weights and biases, whether they're in the RBM or the RNN, to minimize the difference between the unknown distribution that occurs in the black box and the explicitly parameterized distribution that occurs in the model. Okay, and so if this should have been a big P here, but if this was my black box distribution in the red, and this is my model distribution in the blue, in some sense, what you're trying to do with the training is to adjust the weights and biases so that those two distributions land right on top of each other. So this defines, you can do this by looking at the distance between them, and you typically define something like a KL divergence, written here like a relative entropy. the second, the log of, let's see, the log p log p lambda. I guess that's kind of the important piece in some sense, because that has the parameters in it. But if you look, what you're really doing here is if these two distributions in some sense are equivalent, you have log of 1. So you would know if you have perfect training, you would get a 0 for the KL divergence. But what you're really trying to do is just minimize the KL divergence, and it's equivalent without deriving it to maximizing a log likelihood, which is the expectation value of log of this bottom of the denominator in the KL divergence log, with data drawn from the black box distribution. Again, this should be a large P. So that defines the cost function. That really defines the landscape that you are trying to sort of, navigate through and find the global minimum of. Again, the global minimum is this is a data-driven thing. You have you only really have access in this log likelihood expression to the data X, which is drawn from the red distribution, and you're taking log of p lambda of that and calculating the expectation value. So just from that data, you can try to minimize this log, or you can try to minimize this, find the minimum point in this landscape by changing the parameters, and that's done through kind of various familiar methods like standard gradient descent, where I calculate the gradient of that log likelihood and so on. Once it's trained, or during training you can do this, but once it's trained, the idea is that you can now generate these pictures of Einstein or Marilyn Monroe. The idea is that you have a model that can generate new instances of data that you would expect could be drawn from that distribution. So if I've trained on some limited data set, like 10,000 measurements of the quantum hard drive, or if I have 10,000 pictures of cats or whatever, you can take a generative model and you can produce new pictures of cats. And this is done, this sampling step, again, just to be technical for 1 second, happens very differently between tractable and non-tractable density models. So in a restricted Boltzmann machine, you have to use Markov chain Monte Carlo, which results in an autocorrelation time between anything that you measure. In a normalized distribution or a tractable density model, like a recurrent neural network or a transformer, then sampling occurs perfectly efficiently. You get perfect independent samples without any autocorrelation from these because of this autoregressive property, which is really just this property that I mentioned here. So this is one reason that autoregressive models like RNNs or tractable density models like RNNs and transformers are being looked at in earnest for this. These samples that you produce can be used to calculate physical estimators. So in this case, you're looking at pictures of, I don't know, Rasputin and saying, yeah, that looks pretty good. What you're doing is using a human mind to evaluate whether or not that's a kind of useful generative sample. But in the physical case, we can actually do much more, I'd say, mathematically interesting things, like calculate physical estimators. So here I imagine drawing X, a whole bunch of samples X from my generative model and calculating whatever this operator is, the magnetization, the energy, the specific heat, whatever the entanglement entropy, whatever it is that I'm interested in looking at in the quantum hardware. And this idea that I can represent a wave function, not just a probability distribution, but a wave function that I've learned from projective measurements is powerful because, it's useful for experiments. Here's a typical optical table that you might have a cold atom set up on. I mean, these things are nuts. They take years or decades to build. And the measurements that people like experimentalists can produce, can be projective measurements, maybe only in a limited number of bases, or they could have further restrictions on sort of, like almost fundamental restrictions on what they can access. And so having a generative model that can learn from very simple projective measurement data, just the pixels of the images that are being produced like by a CCD camera almost here. And then, the ability to train a generative model and then probe it with things like estimators is kind of the important point. It's the idea that we can replace complicated or maybe inaccessible measurements in quantum computing experiments with sort of virtual or virtual quantum computer, a virtual quantum computer that we've trained from the real data. And then, just to show a specific heat as a function of temperature for some Ising-like system, if we know, for example, if we have some models of what we're looking for, which I'm calling exact here, if we have ideas of the ground truth of how we've modeled the quantum computer, then we can also explore the properties of different generative models, like the hyperparameters, the number of hidden units, and how here's a Boltzmann machine with different amounts of hidden units, how these machines converge to accurately represent different physical states. Okay, so you can do a lot of work on studying the generative models themselves and their appropriateness as sort of representative experimental wave functions. So instead of just talking in the abstract, let me show you some concrete results. So this is a cold Rydberg atom quantum computer. Okay, so this is a real experimental quantum simulator, I would call it. So this is kind of in the vein of Feynman. And back in 2017, our collaborators, this is largely done in the group of Misha Lukin at Harvard, with a lot of work by Manuel Endres, who's now at Caltech, realized a programmable Ising-type quantum spin model with tunable interactions and system sizes of up to 51 qubits. Okay, I was back in that laboratory visiting right before the pandemic hit, and that number is now 400. So I'm showing you data for 51 qubits, and here's a typical data set. What this data set is black or white dots resolved, on some sort of camera, and these are the two states of a qubit. Okay, and if there's a fluorescence that you kind of capture in the probe. And so, if there's a black dot, it's the excited state, and if it's if the absence of a dot, I just cut this straight from their paper, is the ground state, or vice versa. And really, what this is a Rydberg system. So this is an atom that exists in its ground state, or can be excited to a highly excited level, kind of with a large radius. And so we call those G and R. And so black is G and white is R, or vice versa, I forget. And there's also, these are atoms that are trapped in optical lattices with a distance that can be tuned, and that distance tuning tunes the interactions in a Hamiltonian like this. So really what happens is something called Rydberg blockade. When the atoms are big, in the Rydberg state, they're big and they repel each other, and so you get some sort of repulsion here between Rydberg states. But I've written this in terms in kind of the idea that it has it has other parameters, including this detuning, which maps it to a transverse field Ising model. So one way to think about this for the physicists out there is a type of generalized transverse field Ising model, and that actually gives us a significant simplification for what I'm going to show. By the way, this isn't just an academic endeavor. We're also in collaboration with a startup that's spun out of this lab at Harvard called QEra. QEra is trying to take this technology and build a scalable quantum computing with Rydberg atoms. And so a lot of what we're talking about here is going to be an integral technology for these types of startups. So just to get a little bit more detail on what we did this last year led by two students, Giacomo Torlai and Brian Timar, who came up and visited the Pickle for a while before the pandemic. He was up from Caltech. So what these measurements what these experiments can do is produce 3,000 projective measurements every time they're run. So that idea of having 10,000 images isn't very far off. I can get 3,000 images of these Rydberg states from these experiments for every parameter. I didn't explain the parameters in the Hamiltonian, but there's some tunable parameters. This data is used by us as a training set for the generative model, just like I told you. And then after training, we sample the generative model and produce estimators. So why do you do this? The reason we do this is because for some physical observables in these many body systems, the experiment can't access certain measurements that are important to characterize the device, okay? Sometimes it can and sometimes it can't. So here's a comparison to ground truth for a smaller system of, I think it's 8 or 9 atoms. And the ground truth, which I've labeled GT in these plots, is really an exact diagonalization over that full 2 to the n Hilbert space. So it's a very large difficult, exponentially large Hilbert space to diagonalize. So that gives us our ground truth. So for example, so here's one estimator from the Rydberg system. I've labeled it. It doesn't matter what it is. It's the magnetization, which actually means the average occupation. So I'm just using the spin variables for this. But if I have I'd say 50 qubits all in the black state, then the average magnetization per site would be 1 or something like that. The idea that everything's pointing in the same direction. And indeed, this is the state for some parameter of detuning, let's call it. And as I tune the quantum computer, the experiment, which is the black line, can actually just, you can easily see how you measure how many of these are black and how many of them are white. And really that's what this is. This is the average number. Okay. So the experiment gives you a very good, measurement of this, and it matches the ground truth that we expect from diagonalizing the Hamiltonian that we want for this model. And here is a restricted Boltzmann machine. So what this is a generative model that we used and trained off of the experimental data, and then generated new, if you will, images, or which we then measured the average magnetization or the average occupation of, and we see that we get perfect matching. Okay. So why is this useful? I mean, we already have the experimental curve. Why do we need to retake that, take that experimental data and push it into a generative model, do all this minimization of the KL divergence, blah, 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 hyperparameters, searches, all these crazy things? Well, because in a quantum computer, as you know, you have other bases or other ways of accessing information. So for example, if I wanted to measure the in-plane occupation or magnetization in the spin language, which means not the occupation along the Z direction, but the Z direction, but along, say, the X direction, this is something that's not explicitly contained in these images. I've chosen a characteristic axis for my angular momentum, if you will, in the quantum mechanical sense. But I can train a generative model and perform that measurement on the machine learned generative model, something that can't be done experimentally. So here's a comparison of ground truth. Again, this is a diagonalization of the Hamiltonian, brute force. And here's a restricted Boltzmann machine that's been trained from the image data produced by this experiment, but then sampled in a way, because we can do this because it's a wave function, it's the full quantum wave function. We've sampled it in a way to produce the desired off-diagonal magnetization. And you can do the same for entanglement entropy and things like that. And as you can see, this is what we're looking for. We found a discrepancy between what's experimentally going on, experimentally reconstructed, and what we expected in the ground truth of the ideal model. And so this is the kind of thing that helps an experimentalist refine their experiment. This is the feedback loop. So we've taken measurements out of the black box, we've reconstructed generative models in the classical computer, and then we've found discrepancies from what we expected. And then, I cut off part of my arrow here. But what we've done is we've fed this information back into the experimentalist, who will do another iteration of the experiment and so forth. And so that's just a proof of principle in some sense of this idea that machine learning and generative models can be used for characterization of hardware, validating the ground truths, and also, just generally designing things. And I just want to mention that I didn't talk for the, quantum computing or the quantum physics aficionados. I really have just mapped the wave function to square root of a probability distribution. And there's a lot of complexities, pun intended, that have to do with the phase of the wave function or the mixing of the density matrix. And that's also part of our research program, which you could read about in this Nature Physics paper. Just one more quick result, just so I don't, just for my friends, because we work a lot on ion systems now. So here's, again, Rajwal Islam's trapped ion hard drive. So these ytterbium ions have an electron stripped off. Here's an image of 8 of these ions. And what we're doing now in his laboratory is actually using recurrent neural networks to predict the Rabi oscillations for the experts of individual ions. So for example, here's, again, just to be technical, projective, these are POVM measurements actually along 4 different directions. So it's just, measurements of the probability distribution, if you will, as a function of time. And here you see a Rabi oscillation that decays. This is a very typical signature in one of these experiments. The gray here is the amount of data that's been used to train a recurrent neural network. And everything past that gray is data generated from that recurrent neural network compared to the ground truth of the model, which is the lines. So as you can see, we get almost perfect time. We're not just reconstructing static data like we are here. We can also reconstruct the time dependence and predict the time dependence of qubits past the time that we've been training. So this is an example of generalization, and I think is a really important proof of principle of the power of some of these autoregressive models. So a lot of our research now is going in this direction, where we're using autoregressive models to try to make predictions of the time evolved states of these quantum computers. So that's it. Those are the kind of examples that I think are interesting, proof of principle. Things are progressing both on an experimental and on a theoretical front. There's many open questions. For example, which quantum states can we actually accurately perform these reconstructions? It would be nice to take data from devices that are claiming quantum advantage or quantum supremacy and to try to reconstruct the states of those. And people like Martinez's group, or his ex-group at Google, who have designed these experiments have I think taken a lot of this into account. So there are definitely difficult systems to reconstruct, just like there are difficult circuits, if you will, to simulate directly. So that is the boundary between easy and difficult in the reconstruction sense is still largely unknown. And as I alluded to, how is the structure of these states, like learning these different states related to the optimization landscape, right? If I try to reconstruct Martinez's experiment, do I get a glassy landscape? If I reconstruct Rydberg atoms, is it smoother? And all of this feeds back into issues that we are very familiar with in the optimization of loss landscapes and machine learning. Again, we're also trying to study what are the best generative models to use. Okay, so I mentioned restricted Boltzmann machines, and I mentioned recurrent neural networks, and there's been a lot of work recently on transformers and other autoregressive type strategies, I think, that are very promising. So again, this is really sort of cutting edge stuff on the machine learning side of things. So just to conclude, I'll leave this up. Unsupervised learning with generative models, we've already used it. It's already essentially hybridized with the projective measurement output of quantum computers in a useful way. And I like this picture where I have a restricted Boltzmann machine, taking, projective measurement data directly off of a Rydberg atom. But that's kind of, still in the future. Really what happens is the laboratories email us the data. But, I think the idea is to have these devices on chip, or at least as close to the experiment as possible to do real-time reconstruction and readout. And then that tightens this feedback loop between black box and the experiment and the conventional computing. And just like subcomponents of your computer control it now, there's all sorts of control firmware and hardware. Really, the goal of this type of program is to take these machine learning tools, these data-driven tools, and implant them directly into the experiment, even with things like neuromorphic circuits, which we know can be trained to act like neural networks and so on. And the big question, I think, is it's still unknown if machine learning really changes the goalposts for what we consider quantum advantage. So, what is intrinsically possible with classical computers. If we adopt this sort of, machine learning, data-driven perspective on bootstrapping hardware, are we going to get a clear scaling advantage, or are these just sort of pre-factors on scaling speeds? And that's kind of an open theoretical question that we're interested in. Okay, so I'll leave it at that. Thank you very much for your time. And Reza will let me know any questions.
Sure. Thank you very much, Roger. Thank you. That was really, really great, informative talk. So much to learn. And now I know how much out there that I had no idea about, that these are all happening and what can do, in designing actual hardware using, all the techniques that you mentioned, and the research that you guys are doing now is really, really amazing. And I'm sure there are lots of people out there who are experts, who are interested in machine learning and listening to this talk, and they're thinking now, like how can they, you know, get into basically this the research that you are doing, the quantum side of the research now, either it being you know, just designing or optimizing or helping with design of those chips, the layer that you mentioned, the physical layer, or you know, if there are applications that, you know, you can run it, I don't know, faster, you can get any sort of quantum advantage, and they want to learn how to do this quantum, the machine learning using, you know, quantum machines, whatever is available, let's say D-Wave machines that now they're available.
Certainly.
How do you see they can get into this field?
Right. So I think the most one of the most promising ways will be to implement a lot of these techniques into pre-existing open source software. So, for example, IBM is QuizKit. I believe has worked with has collaborated with some of my former students on doing on using their open source software. So I believe in their repositories you can see restricted Boltzmann machine used for enhanced estimator evaluation on IBM devices, and also in this, you know, the startup out of Boston and Toronto called Zapata, Zapata Computing. We've also sort of struck up collaborations with them that will transfer some of this technology into their open source tools. So part of it is the idea of democratizing this through the accessibility through open source tools, which I believe is a big effort in my group. There's another software package called Cucumber, QUCUMBER. I should have a plug for it here, but I don't. So that comes from Pickle. So Cucumber is a machine learning, restricted Boltzmann machine based reconstruction software that's available open source. And maybe we can provide a link to it or something like that. So I think there's lots. I think open source tools that use this type of strategy are a really good way to kind of democratize this or introduce people to the ideas.
Fantastic, fantastic. So yes, if anyone is interested, they can look, I'm sure, at your research page, and there will be more information and links about those Cucumber and Pickle.
Yep. Absolutely. Kind of look for Perimeter Institute Quantum Intelligence Lab, and I think there's links for the software there.
Fantastic. Thank you very much, Roger. There was a question. Okay, I will read the question to you. Could you explain the initial training data you used again, please?
Right. So let me take an example. Training data for us is just projective measurement data. So the quantum state, you know, exists in a superposition like this, and one measurement, you know, of the quantum hard drive you will produces just bit data, just zeros and ones, but it produces it with a probability. And yeah, I guess I failed to mention, but what we're doing is we're associating this probability distribution with the wave function that we're interested in reconstructing. So I think that's what I put on here. So here's a wave function that's related to square root of the probability distribution. Okay, so we're interested in reconstructing that distribution. We have access to projective measurement data, and you know, we get one instance of the data every time we do a measurement, and then we do a measurement 10,000 times. Or in the case of the Rydberg atom simulator, let me just find it here. You know, this is a projective measurement data on qubits. It's just zeros or ones. You know, this is their hard drive. Here's 4 measurements. They have some other correlations they're looking at. We get 3,000 projective measurements, which are just these ones and zeros, and that's what we train on. So we train directly on the state of the qubit, you know, in that basis. And again, what I glossed over, because I don't expect everyone to know a lot about quantum mechanics, is that there's a preferred basis that we're thinking about here, and that's the Rydberg occupation, whether or not you're in a ground state or a Rydberg state. And so that's kind of something that underlies every time, you know, the data, anytime you measure a quantum device, is that you've actually chosen a basis with which to make these measurements. But ignoring that, basically, this is the measurement data that we use.
Okay, fantastic, fantastic. Thank you very much, Roger. The hardware picture you just showed us, the classical one versus quantum. would you mind if
Say up here?
Yes, exactly. Why is it so hard? Like we built that classical, hard drive many years ago. Why is it so hard to build a quantum hardware?
Well, I think the bottom line is that, there are errors that accumulate in classical hard drives, but each one of these squares that I've written isn't a single atom. It's not a single magnetic, dipole. It's actually a collection of many different either atoms or magnetic species or something like that. And there's a huge redundancy here. And that redundancy is baked into a classical hard drive because, there's a lot of errors that can occur. And the errors come from thermal vibrations, or they come from a cosmic ray literally cosmic rays were one of the last errors that they got control of, flipping individual atoms. And so that redundancy and the error correction involved is fairly simple in a classical case. I mean, you can just imagine having 3 different magnetic species, and if they all point up, that's a logical qubit black. If they all point down, that's bit. If they all point down, that's a logical bit white. And then if a cosmic ray flips one of those, right, then it's not a big deal, because you look at the majority and say there's still 2 up and 1 down, and you can correct that error. Now here, error correction is much more difficult, okay? You can see that right away, because you have qubits that, you can't just take a classical readout of, say, bit number 7 here and expect it to be sort of a representation of the state of that wave function, because, that bit in this element of the superposition, or that qubit, could be a different state. And so the process of correcting errors on a quantum computer is much more difficult. And then you couple that with the fact that these things are very delicate systems that have to be isolated from the environment, and things like vacuum chambers and dilution refrigerators. And this all compounds. So they're very delicate. You only want to access them with measurements kind of in very specific ways. But there's lots of cosmic rays, and there's lots of thermal vibrations that are affecting these systems. So, I mean, when I say it like that, it doesn't sound fundamental, but there's still a lot of work to be done to demonstrate that the concept of error correction, in the way that we understand it classically, can also be implemented in a reliable way on these quantum hard drives. So we're not there yet.
Okay. Thank you very much. Thanks, Roger. It's already 1, but I will ask you one final question. You suggested that 400 qubit quantum computer at Looking Group, now they are up to 400, right? The number of qubits.
Yep.
From 51. So in general, just very broad, what type of problems you think you can solve with 400 qubits?
I think in this case, there's a lot of interesting problems that you can prepare in these Hamiltonians, especially if you go to different lattices. What I've sort of demonstrated here is like a one-dimensional array of Rydberg atoms. But once you get to hundreds or thousands of these Rydberg atoms, you can basically stabilize phases of matter that are exotic. And I know that that's one thing we're interested in. It's phases of, in the proper, liquid, solid, gas lingo, you can stabilize phases of quantum systems once you get to a large number of qubits that we don't see in nature. And that's kind of a probe, I'd say, that is true to the heart of what Feynman originally envisioned. It's really that we're simulating or emulating a very highly non-trivial quantum many-body systems that we can't simulate on a classical computer directly. And so that's pure discovery. That's really pushing the boundary or pushing the frontier of quantum many-body physics. And that's what I'm most excited about in these types of near-term experiments. Great.
Fantastic. Thank you very much, Roger. Thank you for your time. And I'm sure there's so many questions and so much to learn. So I just suggest to look at Roger's research page and at University of Waterloo, also Perimeter Institute. There's so much information there, and I'm sure if you reach out to him, he's happy to answer any questions you guys might have.
Absolutely. Thank you, Reza. Thank you, everyone.
Of course. Have a great day or night, depending upon where you are, everyone. And please join us for the next talk on ASIC. Thank you.